Now, relatively short class this morning, just taking up where we left off the last day when we were dealing with graphs, okay? And well done to those of you who sent in your graphs. Your graphs were perfect. I've sent them back to you, and full marks on your graphs. Keep in mind, very, very important, full page, labeled axes, properly appointed points, or properly 3, 2, 1, 0. Now, just to take up from where we left off the last day, today is a relatively short class because it's just feeding on from what we looked at the last day in terms of your graphs. And well done to everybody who sent in your graphs. Your graphs were well drawn. And again, just a couple of pointers to remind you that your graph must be a full page. The axes must be labeled. The points must be plotted properly, okay? Very, very important that you put them down as carefully as possible. And then the best curve that you can get through those points, the better the curve, the more accurate your answers are going to be, okay? So again, it just takes plenty of practice to make sure you understand what we're dealing with. Now, following on from that, the last day's class, I gave you a set of data in 2 questions. I asked you to plot the graph, and all I wanted you to do was to tell me what the average rate of reaction was. And the average rate of reaction, if you can remember, the average rate was the total quantity formed or lost. It doesn't matter whether you're actually measuring something being formed or measuring something being lost. It's the total quantity formed or lost over the time taken. Okay, so for example, if it's a case that 240 centimeters cubed of hydrogen gas are produced in 20 seconds, well then the rate is easy. The rate is 12 centimeters cubed per second. But that is the average rate, okay? Now, if the average rate was good enough, then we wouldn't need to refine this any further and do what we're going to do today. And if the average rate was good enough, very, very few people would ever get speeding tickets or penalty points because of breaking the speed limit. Now, I want you to think of something. I want you to think about why they have squad cars on the road with cameras, or why they have the speed vans on the roads, okay? Are the speed vans interested in your average speed? So in other words, do they stop you and say, where are you going? And I'm going to Galway. How long do you hope to get there? In 3 hours. And then they do a calculation and say, oh, your average speed is whatever, 87, you're fine, on you go. No, they're not interested in your average speed. They are interested in your instantaneous speed. They want to know what speed you're doing now. So they more or less freeze time and they work out at that moment what speed you're traveling. And that's what I want to do in this little class today, is to try and figure out, can I find out anywhere on that curve what the rate of reaction is at one particular point. So not the total quantity of gas formed divided by the time taken, not that, that's the average one. But what is the actual instantaneous rate of reaction at a given time in that particular production of a gas. And that's what I want to look at here. So just as I said already, if average rate was good enough, then a lot of people would escape penalty points for speeding. So in other words, as long as you did Dublin to Galway, which is 270 kilometres, in 3 hours, you're fine. Because your average speed there would be 90 kilometres per hour. Not breaking any speed limits. However, don't forget that there's traffic lights. Don't forget that there's motorways. Don't forget that there's 120 km per hour speed limit on those as well. So you're varying. As you travel from Dublin to Galway, you're varying your speed. At one instant you could be doing 120, at another instant you could be stopped at traffic lights, okay? So we're not, taking the overall picture in chemistry is not really a good enough thing. It's far better to be able to take snapshots of what's going on at every moment in a given chemical reaction. And that's what I want to take a look at here. In the case of speeding cars, the speed at a given instant in time is of far more importance than the average speed of a given journey. So we're taking photographs of a moment in time and you're working out what speed is the car doing at that moment in time. Okay, and the little computer that's inside the van, together with the little camera that takes the photograph, they can calculate very, very accurately what speed you're doing as they photograph you passing by. Like that. There she goes. Okay. So in chemistry, the same thing. The instantaneous rate of a chemical reaction is the rate of that reaction at one moment in time. Now, please need you to get this sorted out in your head. What's the difference between the average rate and the instantaneous rate? The average rate, you have to wait for the reaction to finish. You've got to measure the total quantity of gas formed, and you've got to divide it by how long it took to form that gas, like you did in your previous questions. But for the instantaneous rate, you have to pick a moment in time to pinpoint, and then try and figure out at that moment in time what is the rate of reaction there and then. The same way as photographing a car on the road and trying to figure out what is its speed at that moment. We find it, very, very simple process, by drawing a tangent to the graph at that given time. Now I'm going to go through that here with you in a second. Then you take the coordinates of a point above and below the point of contact. Now what I would say to you there is I can even further refine that, okay? You take your point in time, you find it on your curve. You then, to the best of your ability, draw a tangent to that particular point. And all you've got to do then on that line is work out its slope. And the slope of the line to that point in time on that graph is the actual instantaneous rate of reaction. Now, what does it look like? Well, here's what I want to do. Here's a question where I've been asked, work out what is the instantaneous rate of reaction at 40 seconds. Now, obviously, you're going to do the same thing again. You get your table, you plot your graph, you label your x-axis, you label your y-axis, you plot your points extremely carefully, and you do the best curve through them, and you end up with something like this. Okay? So there's your title. Good. Your x-axis is labelled, your y-axis is labelled, your points are very well plotted, and your graph is the smoothest curve that you can get through there. Okay? Now here's what I want to do. I want to work out the instantaneous rate at 40 seconds. So the first thing I've got to figure out is, well, where is 40 seconds in this curve? There's 50 seconds, there's 40 seconds. So what I need to do, there's 40. So I'm going up along that line there until I hit the graph. So there. That's where I want to work out the instantaneous rate of reaction. Okay? Now, once I find out where 40 seconds is on that graph, I then, to the best of my ability, draw a tangent. Tangent is a line that touches the curve once only. See? So there's your tangent. Now, this is just done on computer screen, so it's not going to be very accurate, but that's what it would look like. So there's your tangent. Now, once you've drawn a tangent to that point, your only job afterwards is to work out the slope of that line. So here's what I would suggest. Move along the line and find 2 points that are easily readable. So there's one. There's 1 point that's easily read. Okay? Now keep on going until you find another point that's easy to read. There's another one. Okay. So what are the coordinates for this point here? 10. So that's 10 seconds. So 10, 90. So my first point is 10, 90. My second point, this one here, is 100 and 210. So 100, 210. And all I have to do then is apply the slope formula. So the slope, which is the rate, is equal to y2 minus y1 over x2 minus x1. So y2 minus y1, 210 minus 90 over x2 minus x1, 100 minus 10. 210 minus 90, so you can get your calculator to do this for you. If I can find my calculator. Here it is. I'm not going to waste my brain cells. So 210 minus 90 gives me 120 on the top, divided by 90. So 120 divided by 90 gives me an instantaneous rate of 1.33, what are we dealing with? Centimeters cubed per second. So in other words, at that moment in time, when we're 40 seconds into the reaction, at that moment in time, if you were to take a photograph, the rate of reaction would be 1.33 centimeters cubed per second. All right. So what did I do? First of all, identify the time at which you want to find the instantaneous rate. Find that time on the actual curve. So run along the x-axis until you find the time and find out where it's represented on the curve. Mark it. Then draw a tangent to that point, and then along that line, along the tangent, find 2 easily readable points and write them down. When you've written the points down, don't forget the first point is x1, y1, and the second point is x2, y2. So when you've got your 2 points, then just apply the old slope formula. y2 minus y1 over x2 minus x1. And by working out the slope of the tangent, you are actually working out the rate of reaction. So the slope of the tangent is equal to the rate of reaction. And even better than that, it's equal to the instantaneous rate of reaction. Now, I just want to show you that the instantaneous rate at 40 seconds is very different from the average rate. Let's work out the average rate as you did the other day. The average rate is the total volume produced. Well, we've produced what? It hits a flat line here where I get 200 centimeters cubed, isn't it? 200 centimeters cubed formed twice. So there's my endpoint. Okay, that's 200 centimeters cubed formed in how many seconds? Formed in 210 seconds. So my average rate is the total volume made over the time taken. And don't forget, the first part of the flat line is where the reaction finishes. So 200 divided by 210 will give me an average rate of 0.95 centimeters cubed per second. So very, very different from the instantaneous rate at that point t equals 40. Now, I have that done here, so I'm going to go through it again. Draw your tangent at t equals 40. So there's the point I'm looking for. Let me just do that again. Let me go back a step. Okay, step number 1. Where do I want to work out my instantaneous rate? At t equals 40. Find it on the x-axis. There it is. There's 40 seconds. Find out where 40 seconds is represented on your graph. There it is. Okay, next, draw a tangent as best you can to that point, like so. Next, take 2 points, easily readable points on that line. Okay, so let's take this point here and this point here. Okay, now let's take their coordinates. This point here is 0, 50, 60, 70, 80, about 0, 80, roughly. Okay, and this point here is 110, 220. So you've got 110, 220 at that point, and this one here, 0, 80. So take those 2 points together, all right? So 110, 220, that's the first one, and 0, 78. Well, it's 78 because I suppose a little bit less than 80. But again, you'll be using graph paper, so you should get a very good idea as to what the coordinates for that point are. You then apply y2 minus y1 over x2 minus x1, all right? So 220 minus 78 over 110 minus 0. So 220 minus 78 over 110 minus 0. And that's done down here for you. 220 minus 78 is, sorry, minus, what did I say? 78, yeah, is 142 over 110. And 142 divided by 110 is 1.29 centimeters cubed per second. Now, it's very unlikely that everybody's going to get the same instantaneous rate at the same point, because all your tangents will be different, slightly different. But there's a margin of error. You're allowed a certain amount below the actual answer. You're allowed a certain amount above the actual answer. So as long as your answer is within a given range, you're going to get full marks. Okay? So, instantaneous rate. At what time? Find the time in the graph. Draw the tangent. Take 2 points off your tangent. Use the slope formula. Work out the slope, and the slope is equal to the instantaneous rate of reaction at that point. Now, I've got 3 questions that I want you to work on in the remainder of this class. Okay, that's all I'm going to do for today, the instantaneous rate. There's the first one. Now you can pause and work. There's the second one. Pause again and work on that question. And there's the third one. So again, you can pause your video now and work on this question. When you're finished, I want you to upload your 3 graphs and your answers to Google Classroom into the space that I've allocated for these 3 graphs, and I'll get them corrected and sent back to you. But it is vital that you understand the difference between the instantaneous rate, which is a tangent, and the average rate, which is just the full quantity of gas produced divided by the time taken. This comes up almost every single year, and it's a lovely question to be able to do quickly. Draw the graph, label your axes X and Y, plot the points carefully, best curve through it, put the title on, and then do the instantaneous rate by finding the time in the graph, drawing a tangent, taking 2 points, and applying the slope.